Yeah, so welcome to this talk by Anish Agarwal. So he's an assistant professor at Columbia University. Previously, he has had postdoctoral stints at Amazon, and he was Simon's postdoc at UC Berkeley. And he obtained his PhD from MIT ECS, working with Alberto Abadi, Devavrat, Shah, and Muntar Dale. So let's have start.
Hi, everyone. Thank you for having me. Today, I'll be talking about the intersection of two interesting fields. One is causal inference, which comes a lot from econometrics and economics. And the other one being, can you hear me in the back? Okay. And the other one being matrix and tensor completion, which is a field maybe that's more familiar to all of you in statistics and computer science. This is joint work with Muntar Dale and Devavrat Shah, who are my advisors at MIT, and Dennis Shen, who is now about to start his faculty at USC, but was also a PhD at MIT. So matrix completion, for those of you who don't know it, the general setup for it is recommendation systems like Netflix or what have you. So rows are different users, columns are say different items or movies in this case. And because the number of movies is very large, each user is probably rated a very small number of them. And so you have a very sparse snapshot of the ratings. Okay, so for example, user one is only rated 2 of the, in this case, 6 movies. And you want to know what would happen to this person if they rated some other movie. And that problem of imputing the entries of this matrix essentially helps you understand what rating someone would have given to a movie had they watched it. Okay, so this is ubiquitous in application for matrix completion. And the question is, can we recover these missing entries? And this idea of recommendation system shows up everywhere, right? You have it for movies, you also have it for items and quotes, and Amazon uses a ton. And if you actually look at real world data and the way the missingness pattern in actual data looks like, it starts looking a lot like this, where you have these clumps of entries that are observed. So some users will rate a lot of movies that are of the same type. Say, you know, I like romance movies, I'll only rate romance movies. And someone who only likes action films, only watch action films. You kind of see this block pattern showing up, okay, in a variety of different applications, from movies to items to what have you. And so what you see is this kind of block sparse structure showing up. Another place that shows up a lot is economics and policy valuation. So one thing I hope to leave you with is that this field of matrix completion is not just about recommendation systems. It's actually much broader than that. I'll give a very few snapshots of things that fall into this space. One where I come from as well is economics and policy valuation. For example, rows here are individuals, columns are time, and over time you get into some intervention. So say you get into Medicare in the US, which is like a government medical program, or you do pilot studies, like for example, in some cities, I will introduce a new kind of, like for Uber, I'll introduce a new kind of ride sharing policy. So they do it normally in a staggered way. So they don't always introduce everything one at a time. At one time. And so what it leads to is this kind of staggered adoption pattern. And what you want to generally know in these kinds of settings is what would have happened to, say, an individual or a city if they'd stayed in the regular intervention. Had they not moved to the new intervention, what would have happened? This is a kind of factual question that people care about. Okay, and what you see is that a lot of in economics and in policy valuations, kind of staircase structure is what shows up. Another place that you can think of it, if one's phrased correctly, is contextual bandits. So you have discrete states and discrete actions. You can think of columns as state, rows as actions, and then each entry says the reward for that given state and action. Okay, and then let's say I ran some bandit algorithm to minimize regret. What you'll tend to see is this kind of structure, where you'll see where they will try to explore areas where there is some level of high reward, and so they'll explore that space. Places where they don't explore, they'll think, you know, there's hardly any value there because it's going to be mostly low reward settings. But you can kind of think of it as this matrix where you have states, actions, and rewards, and you want to figure out what would be the reward for a given state and action. Okay, and so you got to see this piecewise block structure showing up in these settings. And so what I want to first leave you with is that matrix completion can encode a wide variety of applications. From just the 3 would be recommendation systems, which are classical, staggered adoption settings that are like policy settings in economics and large-scale engineering systems, and also things like contextual bandits. Okay? And so the goal across many of these settings is to impute the missing entries and also to denoise observed entries, because you can think of each entry which you observe is also noisily observed. Okay? And the problem to finding a matrix completion algorithm that works in a unified way for all these different applications is that different applications induce very different sparsity patterns, as you can see. Okay, so getting an algorithm that works in general for all these different sparsity patterns is a challenge. Okay, so the thing that we hope to do here is to reason about different sparsity patterns through this language of causal inference. So one, if you ask people, say like Don Rubin, who is a famous statistician, you ask him what is causal inference about, he'll say, well, causal inference is about it's a missing data problem, because you're missing counterfactuals. And matrix completion also is a missing data problem. And there's a nice correspondence between many key ideas in these two fields. In causal inference, you can think of, say, estimating potential outcomes. In matrix completion, it's imputing missing entries. In causal inference, you have this idea of confounding, confounded data. I'll explain what that is. And then in matrix completion, that leads to having missing, not at random data. And then in causal inference, you reason about different kinds of studies, like you have observational studies or experimental studies. And what that leads to in matrix completion is having different kinds of sparsity patterns in the appropriately defined matrix. Okay. Continuous means that there are a continuous number of individuals, and yeah, absolutely. So that's also definitely possible. And there's extensions of both sides to that. For example, with matrix completion, you go to things like graph-on estimation and things like that. Yeah, there's a variety of ways that people do that. But you normally start with this problem, and you can high-level extend. Mm-hmm. Absolutely, but I think what you'll see is that when you have a matrix, and what happens is that as long as there's some structure to the underlying function, that matrix becomes low rank. And that low rankness, where the rank of the matrix is a lot less than either the rows or the rows and columns, that's what lets you share information. If you only had one vector, then that would be difficult to do. Yeah, sure. Yes. There's a question there. What does that mean? It could be both. In the Medicare, for example, the adoption is given by the government, right? Sure, but both of those things can fit in. There's no problem. Both can be fit in, but that's a good, where you're going is good, because what you have to reason about when you think about missingness is what caused the missingness. Why did one entry be seen and another entry not be seen? And you have to reason about those types of things. So reasoning about who gave the intervention, under what information were they using to decide what was missing, not missing, is very important when we think about causal inference. So the framework can handle it, but as we think about different algorithms, the question you're asking is a good question to ask. Yeah, please ask any more questions. Yeah, no problem. Yeah. So just to give a formal setup for what matrix completion looks like. So you have this expected matrix M, right? That's an M by N matrix. There's some random outcome Yij, which is equal to Mij plus epsilon Ij. Okay, and then you have this binary mask matrix A, okay, which is 0, 1. So if Aij is equal to 1, then you observe Yij, which is the noisy matrix. And if a noisy entry, if Aij is 0, then it's missing. And the goal is that given this Y tilde and A, can you somehow recover M hat, which is close to M? Okay, and the entry that we care about can vary. Could look at the Frobenius norm, which is an average over all the entries, the operator norm, the infinity norm, which is the entry-wise error, which is the strongest notion of error here, etc. And so normally when we think about matrix completion, we just worry about one form of missingness, which is missing completely random, which I'll talk about. But here, as we think about different sparsity patterns, we have to think about different models of missingness. Okay, and that's really what this flavor of matrix completion is going to be about in this talk. So you have this Y, which is this matrix of potential outcomes, or different outcomes. A is this matrix which determines what entries are missing or not observed or not missing. And the question is, under what conditions is Y independent of A? So the two models that have been studied so far, and this kind of has been laid out by Don Rubin of different models of missingness. The two that have been really studied so far is missing completely at random, which I'll explain in a second. The second one is, it's called missing at random. And there's been more extensions of it. So I'm just going to call it literature missing not at random, or LMNOR. Okay, this is a phrase I've come up with, so you won't find it in Google. But missing at random is what you'll find in the web. And then the third one is missing not at random. And I'll explain what these three things mean. But before I go there, yeah, sorry. You were asking something? Oh, okay, sorry. So before I explain what those methods are, let me just say that so far the work that's been done in literature really stops at this LM-NOR. And I'll explain what that means. So Ma and Chen, they're at Carnegie Mellon. They say in terms of theoretical analysis, this is probably the best paper I've seen in the last few years that first talked about this missing not at random problem. They said we've not addressed the full generality of MNR data in matrix completion. They say our theory breaks down when the probability of observation is exactly 0. So for example, in recommendation systems, their algorithms would not work if, say, a vegetarian will never go to a steakhouse. Right? They also say that we still assume that each entry is revealed independent of other entries. So for example, in the Sager adoption setting, if I tell you that an entry is missing at time t, that's also missing at time t plus 1. And so that wouldn't hold. This kind of sparsity pattern wouldn't hold with what they can handle so far. And they say these are two open problems amongst many. And I'll go into what that means. And similar assumptions are made in work that have followed up this work, for example, by Bhattacharya and Chatterjee at Stanford, and then Yang, Deng, Wu, and Odell at Cornell. Okay. Plus, most of the results that occur, they generally recover Frobenius norm recovery. So on average over all the entries of the matrix. There are very few results for entry-wise recovery of the matrix, which is what you ideally want, because that means you can recover every entry of the matrix well. Okay, so I'm making a big hoo-ha about does the missingness model matter? Okay. But maybe existing algorithms as they are that people have studied in the literature, maybe they just work. Can we use them? Here's a very, very simple simulation we did to argue that it doesn't work. We took an 80 by 80 matrix. It was rank 5. Okay, no noise. Okay, so the only form of corruption is missingness. And we created 3 different missingness patterns. The first is missing completely random, which is what people study in the literature normally, right? And here what you say is that each entry A, ij is equal to 1 with probability p. So you flip a coin independently for every entry of the matrix. If it's heads with probability p, then you see it. If not, you don't see it. And this is kind of standard model of missingness that people have studied. It started with, say, Candace and Tao in 09, Candace Rect, Martin. A lot of people have studied this work, and it led to beautiful statistical results. The second model is what I call LMNOR, and the basic idea is now the propensity of the coin, the bias of the coin can vary across different entries. Okay, so Aij is now equal to Pij with probability 1. Okay. And this is the model that I talked about earlier that Ma and Chen had studied, Bhattacharya and Chatterjee, and Yang et al. Studied. And then there's this third model, which I call missing not at random, where we kind of break the key assumptions required in LMNOR. In particular, we allow the entries to be 0 with probability 1, or the probability with probability, they can be dependent on each other, which entries you see. So Aij can be dependent on AKL. And then the matrix M, which is the underlying expected matrix, that can be dependent on A. So the flip of the coin can be dependent on the actual underlying expected rating. Okay. And this is the model that we're going to study. Okay. So just a simple simulation that we did. So in light blue here, this distribution is the true distribution of all 80 by 80 ratings. Those are 1,600 entries. I just plotting the histogram of that. And now we did is that we said, okay, let's do the MCAR sampling, right? Okay, with approximately 30% observed. And so that's the dark blue. And you can see that up to a normalization, they look like each other, as you'd expect, because it's completely, the sampling of what you see is completely unbiased. Right? And the goal is that given this dark blue distribution, can you recover the underlying true distribution? Okay. First question one could ask about matrix completion is, can you do the simple task? We ran a few different algorithms. The first algorithm we ran was a very popular one in literature called Universal Singular Value Thresholding, USVT by Chatterjee. It's a very popular spectral filtering method where you kind of do PCA. And actually, surprisingly, it didn't work. It tended to just recover the mean for some reason. So though it is designed for this style of missingness, it for some reason didn't work. But the good thing was that we tried another method that's very popular in the literature called soft compute by Hasty et al., also at Stanford. And this is a kind of an optimization-based method. Okay. And it actually worked beautifully, right? The dark blue that was recovered is kind of completely covering the light blue. And that's what you would hope to see. And another approach that we'll talk about later is which I call synthetic nearest neighbor. That's the method that we're going to talk about. That also does a good job. It kind of is covering the light blue. Okay. I mean, we can quantify all this, but visually trying to show you what's happening. Any questions about the simulation? It's exactly this setting that I said here. So 80 by 80, rank is 5. No noise, there's no noise. Yeah, so LMNAR is where the flip of the coin for each entry ij is different. Here it's uniform, all right? And then here I'm breaking the key assumptions at LMNAR where I allow the entry to be 0, observe with 0 probability. Whether you see one can be a function of another one, right? Versus the coin flips are independent of this one, and so on and so forth. Any other questions? Yeah. Yes, exactly. That's it. It should.
You had the number of lower than.
No, this is actually very high. There's 30% of samples. It should. We were surprised as to why it didn't. Yeah, I don't know why it didn't. Then the next thing we tried was with LMNAR, where you have a different bias of the flip coin for each entry. And USVT still didn't do very well. Again, kept tending towards the mean. Soft compute is working decently well, actually. So, I mean, it's not as perfect as it was the last time, but it's still doing a decent enough job. Where the dark blue is kind of covering the light blue, but there's still a little bit that's missing. And then we tried the synthetic nearest neighbor, where it was working quite well as well. And the only reason I'm saying this is because in this algorithm that we applied, we thought very carefully about missingness and under what conditions of missingness this algorithm works. Okay, so great. So soft compute is still working kind of well, but now let's go to the MNAR setting where we kind of break the key assumptions, right? Like you observe things with 0 or 1, dependent, etc. So USVT doesn't work, but to our surprise, soft compute completely stopped working. As I switched from LMNAR to MNAR, right? It's tended to just recover rating 1 for some reason. So you can see how sensitive these different matrix completion algorithms are to how things are missing or not missing. And I wouldn't show it to you if it didn't work, but SNN was still working, where I was recovering the light blue really well. But robust meaning what? To this kind of thing? Not really. So that's kind of what we're exploring. And we're trying to use the language of causal inference to reason about it. Yeah. So we tried all of these. So I would say this was the soft compute worked the best of the lot. Yeah, so we tried like the nuclear norm minimization. We tried the alternate least squares. Yeah, we tried the whole plethora of things. And I'd say soft compute is what generally worked the best of all of them. So when I get to the assumptions, I get to the theory, we'll talk about it. Yeah. So there's an analog of the incoherence assumption, which incoherence to me is about the signal being well spread in some sense. And there's an assumption that'll show up that it's not the same, but it's analogous. Yes, exactly. That's kind of what it's doing. It's a bit of a twist on that, but yes, it's kind of like an optimization. Nuclear norm, you can think of it as like the matrix version of the lasso style, what they're doing. Yeah. So we'll get to the algorithm in a second. In this setup, the way things are missing is that I said that, for example, if the rating is above, I made the ratings between 1 to 5. If the ratings are above 4.5 or below 1.5, then you see it with probability 1, otherwise you don't see it. And then we did some other correlations where, for example, if enough things in a certain column are seen, then I'll see some other thing. So there were a few. The basic thing was that if your ratings are very low or high, then it's seen. Otherwise, it's not seen with probability 1. And then we added some more correlations. For example, if this user had seen it, then another user will have to see it. We are not using that information as algorithm. We're using that information to create this missingness pattern. I haven't gone through the algorithm yet. I'll go through the algorithm, and then you'll see what the algorithm is. There's a question? Okay. And so just to state, this is an important problem because nowadays you can see recommendation systems are everywhere. And the data really is MNAR because the way these things are being recommended to you and the way people rate things, there's a great amount of bias in there. So you have to be very careful when you're using these kinds of algorithms, which people are, in practice when imputing missing entries. Another place where I've been thinking about it a little bit is the US Census. There's been a lot of work in applying machine learning to the US Census for a variety of problems. But it's interesting because 40% of data is missing for a lot of interesting, important fields like income, sexuality, etc. And so again, you have to be very, very careful about thinking why things are missing if you want to use these. In the census? Yeah, we've had a few. So, but I'll tell you about it offline. Yeah. Okay, so now I'll go to the algorithm. So the algorithm really is very simple. It uses two ideas. The first idea is something called nearest neighbors, which is probably familiar to a lot of you. So let's say I want to fill in, this has been new at Berkeley. I want to know what would happen to her if she had rated up. Okay, so I look at people who are close to her. That's one of her postdocs, Yen Shah. I say, okay, they have had at least 2 ratings that are similar. Okay, but he rated up, and so I'm going to say Bin also rated, gave that 4 stars. Great. Then that's one nearest neighbor, and that's it really. There are all sorts of interesting varieties of this. You can do k nearest neighbors, what's the right distance, etc., etc. But at a high level, that's what nearest neighbor is. There's another idea that comes from econometrics called synthetic controls. It was proposed by Alberto Abadi in 2003, and then there's been a whole literature about it nowadays. And ask the question of, say, like ask counterfactual questions. Like, what if California never proposed Prop 99, which is a legislation on tobacco? And so, for example, that's the type of policy thing we talked about, where at this time, California introduced Prop 99, and so its outcomes without Prop 99 or under control are missing. And I want to know what would have happened to California had it remained under control. So it's a very simple algorithm. What you look is you look at the outcomes of California before the intervention happened, like it's cigarette sales. You write it as some combination of the other 49 states, because we know they didn't go through this as Prop 99. You get that linear combination. Abadi proposes using convex regression for a variety of reasons. And then you apply that convex model you learn to X2, and then you get that imputed outcome. Beautifully simple algorithm. It's used everywhere. Okay, at Amazon, I cannot tell you the number of teams are using it. Everywhere it's used essentially. And there's a variety of different extensions that have come out of it now. But this is the basic idea. X1 are basically the pre-intervention outcomes. So this is the matrix of cigarette sales. So I want to know what would have happened to California's cigarette sales if they hadn't passed Prop 99. So X1 is the outcomes of the 49 states' cigarette sales for 10 years before the legislation went into place. X2 is their outcome after it went into place. Y1 is the outcomes of California before it went into place. And that part is missing, right? Because I don't know what their cigarette sales would have been had they not gone under Prop 99. Yes, and you write California as some synthetic combination of those states. Yeah. Absolutely. So I'm not going to go justify synthetic controls because that's not what this paper is about. I'll talk about the assumptions that make our algorithm work, and it'll answer your question. And so what synthetic nearest neighbor is really a simple joining of these two algorithms. Okay. So say I want to impute entry ij here. Okay. What it does is that it first looks for a fully observed submatrix X. Okay, such that the corresponding elements of it in row I are observed, which is AC, they call anchor columns. And the corresponding elements of it in column J are observed. We call it anchor rows. Now, if you just look at the AC, XAR, and the question mark, that looks a lot like the synthetic controls problem, right? And that's all we're really using. Now, what we do, the little trick we do is that the X, we divide it up into K different blocks. Okay? So we X1, here I'll just do X1 and X2. And what we do is we learn a linear model between Y1, which is that part that's fully observed, and X1. And the way we learn the linear model is through principal component regression. We first do PCA on X1, and then you do OLS. Okay? And this is why we call a synthetic nearest neighbor, because there's no other row that looks like you, or we're saying some other combination of rows, some other linear combination of rows looks like you, hence the synthetic nearest neighbor. Okay? We repeat that with all the different blocks you create, the K different blocks, and you take an average. Okay, so you take an average of these synthetic nearest neighbors, and that's how you compute this M hat ij. And that's it. It's a simple 3-step algorithm. We're not using any covariates, nothing. We're just looking at the actual observed outcomes. Sorry, go ahead, Sandeep. So I'll explain the optimal way of blocking it. Yeah. The way you actually create these blocks, there are multiple ways of thinking about it. One is you can think of it as like a bipartite graph and finding a maximum bi-clique, though that's very slow in practice. What we do is something called spectral biclustering, where you kind of run a spectral algorithm on the mask matrix, and that kind of imputes these blocks for you. Yeah. Yeah, we'll get to the assumption in a second. I'm explaining the algorithm to you. I'll get to the theory in just a second. Correct. So that'll show up in the assumptions, and there'll be ways of testing for that. So this is kind of an instance-dependent thing. So if the assumptions hold for this particular entry, then we can say something. If it doesn't hold, then you can't. Though you can argue, for example, if the columns are being rows and the singular vectors for the rows and columns are being sampled from very natural DGPs, then what you're saying will not hold. That there will indeed be enough other rows such that your row can be written as a linear combination. But they won't be able to deal with the adversarial setting where, say, it's a rank 2 matrix. The first row is has one thing, lies in one subspace, and the rest of them lie in another subspace. It won't work. But you can kind of test for that because you can hold out a little bit of this and see whether you can hold a linear model holds and so on and so forth. Yeah. I'm leaving apart this thing here, you mean, please? This part here. Correct. So in this setting, what we look for normally when you do these spectral biclustering thing, what it tries to find is these big subblocks. And so the thing about this subblock is that this full thing is observed, right? But if I include this thing, then this part of it is not correspondingly observed. Though in technicality, you can use this full thing. Though what these kind of algorithms produce is this fully observed submatrix. That's what we use. Yeah. Yeah, actually, there is highly structured data. So you look at the outcomes I saw at the start. That's what I was emphasizing. You really see these blocks show up in your data. These big chunks of blocks, and then small parts that are missing. And so this kind of structure shows up everywhere in the US census for sure. Yeah. It might be missing, a lot of it might be missing, but you still see these blocks going up. Yes. No, you can run them all in parallel if you want. So it's a good question. So in this algorithm, it can be run in a completely parallel way. It's not a problem. Though one could think of iterative ways of doing this, where you impute first, because then you have this IJ fully observed. You can use that as a way to impute other entries. Correct. But then the error obviously propagates, right? And so that analysis we haven't done. But it's a very good question. It's a really good question. Yeah. Yes. So if you have MCAR data, then with high probability, you'll have these blocks. If it's MCAR, then the matrix of whether it's missing or not missing is observed, right? The A matrix, 1-0 matrix is fully observed. So using that, you can find these blocks. Maybe I'll ask you the question offline because maybe I didn't understand it. But with MCAR data, it works at a high level. So the rates aren't as good as algorithms that are designed for MCAR data. That's for sure. Okay, so when does this algorithm work? So in general, you obviously cannot infer, because there's more unknowns than there are observations. What you generally assume, which is standard in the literature, is you assume that this matrix is low rank. There's a low dimensional column factors and row factors that determine this matrix. So that's given by R. Okay. And then what kind of missingness is allowed? What kind of missingness do we allow for? So we say this Yij, given that low rank assumption, is a bilinear product of Ui and Vj plus epsilon ij. And what we allow for is this kind of DAG, in some sense, which is that the UV, which are the latent factors, they can determine the A and they can determine the Y in an arbitrary way. Okay. But the only thing is that the epsilons, right? What is the Y a function of? The Y is a function of the UV and the epsilon. The epsilon is a random noise. The epsilons cannot have an arrow to the A. Okay, so basically conditional on UV, A and Y become independent. That's really what we're saying. Another way of saying this is that the selection on these latent factors. For those of you who know causal inference, this is kind of analogous to saying selection on observables, so selection on covariates. Okay, but here you don't observe the covariates, but by having these repeated measurements, you're getting a proxy for these covariates using these latent factors. But we do allow for things like the probability of observing something can be 0, the matrix A can be arbitrarily correlated with each other, and then the M can be correlated with the A. So what are we not allowing for? So what we're not allowing for example, is adaptive missingness mechanism. So for example, if I observed an entry like today, and then based on that, I'm deciding whether tomorrow I observe you or don't observe you based on the observed outcome, that'll break this down, right? Because then my intervention tomorrow is a function of the Y today, which means it's a function of the epsilon today. And so this will break down. Okay? So it doesn't allow for these adaptive methods. What it allows for is where let's say some adversary looks at the M matrix and based on that decides which things you see or don't see. That's allowed. No, you absolutely can do that, right? I can make the decision for a particular entry based on, so U in some sense is yeah, all the factors. So it can be completely rating dependent and user dependent, not a problem. Yeah. I don't observe UV, but I'm saying absolutely. But I'm saying it is dependent in the sense that the U's are like heterogeneous across different users, right? And V's are heterogeneous across different items. So in that sense, they can be observed. Correct. That's what I'm saying. So it cannot be adaptive in that setting. Absolutely. Though there are extensions that are coming up like that, but in this base case, you can't. Now, what are the other assumptions that we require? The next one is the span inclusion. So this will go back to your question of when the beta continues to hold. Okay, so what you need is that the expectation of Y, right, that row, that needs to lie in the row span of each of these X's. The fact that it lies in the row spans means there exists a beta. That there exists a way of linearly writing Y as some combination of the X's. The second thing you need, that's really what motivates linear regression. The second thing is that this X tilde 1, X tilde 2, that lies in the column span of X1 and X2. That is what lets you transport your model from your YX1 to your X tilde 1. Okay, so this span inclusion in some sense is our version of why you can generalize. Okay, but there's no distributions really being, no distributional assumptions are really being made on the X's and the Y's, or in expectation at least. The fourth assumption is to do kind of with what you're saying about incoherence. What you really require is that the singular values of X1 and X2, those are singular values that they have. The smallest one, that needs to be a lot larger than the maximum singular value of the noise. So you need the separation of signal and noise. And that's really what motivates PCR in some sense, because the PCA step, what it's doing is that it's denoising the data. So you're getting a proxy for the M, the expected thing, and not the noise. Okay? And you can also think of it as a way of regularizing your data or your fit, right? So you don't, yeah, go ahead. Correct. On the blocks. Correct. Correct. Yeah. Correct. Exactly. So that's what that spectral biclustering step or these when you look at it, it doesn't look like this. Then you apply a variety of algorithms that exactly output things that look a lot more structured. Like with the coat or movie lens example at the start, we saw those blocks. So that's not the way the actual data looks. But then once you permute, it exactly looks like this. Yes. No. They need to hold for whichever instance that you're doing the regression on. Right? Correct. So I guess the way we look at it is that exactly. It only needs to hold the instance in which you do it. Yes. But we're not trying to estimate the UNV, correct? Correct. Correct. Yes. Yes. Though in the end, the results we'll give will be in terms of entry-wise recovery of the matrix. So my guess is that if you can entry-wise recover the matrix, then you could probably output UNV. We don't need to recover the rank. What we do is that we need to recover. Well, what we do is we kind of recover the rank of these x1, x2 matrices, but we don't explicitly need to recover the rank of the entire matrix. So as I said, once you recover impute the whole matrix, you can probably get a proxy for it. Okay, now just to give a sense of, let's say this matrix X was hypothetically of size k cubed by k square. Then what I'm going to do is, the optimal thing to do is to break it up into k sub-matrices, each of size k square by k square. To kind of answer your question of how to break it up. If that is the case, then these are the kind of results you produce. The first is finite sample consistency. That is, for every entry ij that satisfies those four assumptions I just said, your recovery m at ij minus mij is at this rate, which is r, which is the rank of the size of the singular vectors over square root k. That probability. Where k, in some sense, you can think of as the number of synthetic nearest neighbors you have. And again, as I said earlier, you can prove this kind of result even for MCAR data. Okay, you can prove consistency. And the next thing you can prove is that if you appropriately normalize your estimate, you can show that it asymptotically is normal. That's what lets you produce confidence intervals. Okay. And so that's it for the theoretical results. And I'm going to go to more applications. Any questions on the theoretical part of it? Yeah. Adversarial in what? Well, what does that mean? Like, is the noise adversarial, or is the way that it's whether I see it or not is adversarial? So this is for the setting where the noise epsilon are all like sub-Gaussian. So that's what this set of results is for. The setting where where the noise and the missingness pattern are both adversarial is very interesting, but we haven't touched it yet. I do think it's a very interesting thing. So I guess there's a few steps in this algorithm. So the first step is finding those subblocks. So the optimal thing to do would be to find, you can reduce it to a problem of, like, to find the biggest subblock. You can think of that as finding the maximum bike leak in a bipartite graph. I believe that's computationally hard. So, but there are two comments to that. One is that a lot of the applications you see in the literature, they naturally kind of give you these blocks that they show up. So if let's say the data has already been permuted correctly, after that, the only step that is computationally complex is the PCA step, which is what, like cubed, I think, n cubed, and that's it. Yeah. But it's finding this block, which is the most computationally expensive part, at least as approximation. The spectral biclustering algorithms, or there are also maximum bike leak algorithms that work reasonably well, but they're a lot slower in practice. For each I and j, you'll be having a k that is random. Sure. I mean, it's instance dependent. It's like the size of your blocks. So this is saying that if you give me a block of this size, it's kind of instance dependent. You give me a matrix. If you find a block that is of this size, then this is the error recovery I can give you. If you have MCAR data, then you can prove with high probability that you'll find a k that is sufficiently large. This is another assumption in some sense they were making, that there exists such a matrix, a submatrix that is large, right? And what I'm saying is that at least with MCAR data, if you assume that your data is MCAR, then such a matrix will exist with high probability. But outside that, it's an instance dependent bound where I'm saying that you look at the matrix, if such a matrix, submatrix exists, then here's an error recovery. Correct. Where you have a different K for each thing. So this is entry for each ij. I mean, if you want, you can always write a k-min there and say this is the uniform bound for every entry because I have a k-min. But I'm saying for every entry that you see, this is the result I can give you. Exactly. Yeah. Yes. Correct. Correct. Exactly. Yeah, exactly. It's just the UV which we condition on, and then it's an arbitrary mapping from that to A. As long as the mapping is such that this kind of matrix exists, you have a result. So density assumption on so what you need in the assumption that's being placed in the U and B is somehow showing up here, which is that the singular values are sufficiently large. I've tried. I don't know clearly how to do it, but I can only know it at an intuitive level, which is that incoherence to me is about saying that each entry is given by it's a function of many elements of the singular vector versus just one. But I don't know if that kind of incoherence thing shows up here. I don't know. We should talk about it. I don't know the answer. Yeah. Anything else? You can't because your K is going to be small anyways, right? Yeah. But if you look at actual data, what it looks like is you do see these blocks. So that's kind of what we are exploiting. And you can, so at least for the MCAR setting, then at least in the simple 80 by 80 simulation, it worked reasonably well as well. Yeah. Yeah, though, yeah, people have used those kinds of algorithms to denoise images. I haven't tried that. Our setting has been more in terms of learning and econometrics and policy evaluation and recommendations. One could potentially do that. Okay, so just to give you a sense of where a place we have thought about applying this is, say, in experiment design for, say, clinical trials. So normally the way a clinical trial goes is you start with an in vitro study and then you go to a clinical trial. And these are normally inefficient and slow. And so the question is, can you identify the most promising therapies using a limited experimental budget? So say you had M cell types and N therapies, and you want to know what is the effect of each therapy on each cell type. Okay? So I want to recover all M times N experiments, but I only give you a budget of M plus N. What can you do? What cell types and therapies should you experiment on? So you can think of it as a matrix where rows are cell types, columns are therapies. Now, which of these entries should I observe? If I'm actually allowed to design an experiment, which of these entries should I observe? This is the optimal thing to do, given if you're applying synthetic neurostatus, is this L pattern. Why? Because then you're using kind of the same elements to impute all the entries. It's the same submatrix you're using everywhere. And then here you can actually argue that you can recover all M times N experiments at an entry-wise rate of 1 over square root K, given basically M plus N entries, which is kind of like the theoretical lower bound is you need M plus N entries. Again, some interesting things one might think about if you're interested in this kind of work, feel free to talk to me, is what is the optimal kind of experiment design or adaptive experiment design? And also, can you use this kind of technology for, say, inference versus regret bounds in contextual bandits? I think there is interesting work here to be done to bring kind of collaborative filtering methods to bandit literature. There will be a lot of okay. Well, no, I'm going to learn a different, for this cell type here, I'm going to use this part here. The linear model I learned, the coefficients I learned will be different from the ones I learned here. Right? So the linear model I'm learning is going to be different. As a result, the imputed outcomes are going to be different. And actually, there's no confounding here because I'm going to randomly select which columns and which rows to create this L. Actually, there's zero confounding because it's randomized. And because you randomize the selection of the rows and the columns, you can actually show with high probability that the remaining rows and the remaining columns will lie in their span with high probability. So this inclusion and the well-balanced spectrum will hold. Yeah. Sure. Okay, sounds good. So okay, I'll just end with this thing then, which is that one thing you have to do is to think about how do you actually produce those confidence intervals. To produce those confidence intervals, what you need is a way to actually produce the variance of epsilon ij. Okay, so sigma square ij, which is the expectation of sigma square of epsilon square ij, you need to be able to estimate that to produce those confidence intervals. So in general, if it's arbitrarily heteroscedastic, then you can't do that. But one way you could do that is to say, let's assume that the variances of the noise are also low rank. Okay, so if that's the case, then note that expectation of y square ij, that equals to m square ij plus sigma square ij. Okay. And what that leads to is that if you look at this matrix S, right, which is the entryway squaring, the rank of that is going to be less than the rank of m squared plus the rank of your sigma, of your variance. Okay, which is really nice, because what that leads to then, I think, oops. No, it's okay.